The morning of June 1st, 1943, somewhere in the Italian countryside near Naples, American ground troops moving through abandoned Luftwaffe positions discovered something that would change how Allied intelligence understood their enemy's most feared fighter. A Focke Wulf 190, nearly intact, sitting in a field like a gift from the aviation gods. The propeller was bent, one landing gear strut had collapsed into the soft earth, but otherwise, this 7-ton beast of German engineering appeared remarkably whole. Within hours, the find was reported up the chain of command, and within days, the aircraft was being carefully disassembled, packed onto transport trucks, and prepared for a journey that would take it across the Atlantic to Wright Field, Ohio. The Army Air Force's intelligence officers knew what they had. Since August of 1941, when the Focke 190 first appeared over the skies of northern France, it had earned a reputation that bordered on mythical among Allied pilots. RAF Spitfire pilots, men who'd flown with confidence against Messerschmitt 109s, found themselves suddenly outmatched. The German fighter was faster in level flight. It could outdive anything the British flew. Its roll rate was phenomenal. And its firepower, 4 machine guns and 2 20mm cannons on the early models. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Could tear through a Spitfire's thin aluminum skin like paper. For more than a year, the Focke 190 had been the undisputed master of the air war over Western Europe. But there was something else about the German fighter that puzzled Allied intelligence. Luftwaffe pilots seemed strangely reluctant to engage in prolonged combat. RAF pilots reported instances where Focke 190s would make a single attack pass, sometimes 2, then break off and disappear, even when they held tactical advantage. German fighters would bounce Allied formations, make their attack, then zoom away rather than pressing their advantage. At first, Allied tacticians assumed this was simply German doctrine, hit-and-run tactics designed to minimize losses. But there were whispers of something else. Captured Luftwaffe pilots, when interrogated, sometimes mentioned limitations, engine restrictions, time constraints, nothing concrete, nothing that made complete sense. Until this aircraft arrived at Wright Field. The facility at Wright Field, near Dayton, Ohio, had become the primary testing center for captured enemy aircraft. By mid-1943, the sprawling complex housed a bizarre collection of aviation specimens. Japanese Zeros sat next to German Messerschmitts. Italian fighters shared hangar space with experimental prototypes. The Air Materiel Command's Foreign Equipment section had developed expertise in reverse engineering enemy designs, understanding their strengths, identifying their weaknesses, and disseminating that knowledge to combat units. When the Focke 190 arrived in early summer 1943, it generated immediate excitement among the test pilots and engineers. The RAF had captured an Focke 190A3 the previous year, in June 1942, when Oberleutnant Armin Faber mistakenly landed at RAF Pembrey in Wales, thinking the Bristol Channel was the English Channel. The British had flown that aircraft extensively, learning its performance characteristics and developing tactics to counter it. But American pilots had limited access to that captured specimen, and the Army Air Forces desperately needed their own evaluation data. Now, they had an aircraft they could test to destruction if necessary. The Wright Field team began with the standard protocol, external inspection first, documenting every detail of the airframe, armament, and visible systems. The W190 was a study in contrasts. The fuselage was relatively small, compact in a way that suggested efficient packaging rather than spaciousness. The wings were surprisingly short and stubby, giving the aircraft an almost stubby appearance compared to the graceful lines of a Spitfire or the elegant sweep of a Mustang. But everything about the construction suggested robustness. The landing gear was wide track, stable, clearly designed for operations from rough fields. The control surfaces were large and well balanced. The cockpit, when they examined it, was remarkably well laid out for pilot convenience. What struck the American engineers most was the electrical system. Unlike every American fighter, which used hydraulics for landing gear and flap operation, the Fiev W-190 employed electric motors. This was revolutionary. Electric systems were generally considered less powerful than hydraulics, but the German designers had made it work, and the advantages were significant. No hydraulic fluid to leak, no pressure lines to rupture in combat. Simpler maintenance. The entire philosophy spoke to a different set of design priorities. The engine, however, was where things got interesting. The BMW 801D2 was a 14-cylinder, twin-row radial producing 1,700 horsepower at takeoff. In terms of raw power, it was competitive with American radials like the Pratt & Whitney R2-800 that powered the P-47 Thunderbolt. But the installation was peculiar. The cowling was extraordinarily tight, fitted close to the engine with minimal clearance. At the front, a 12-blade cooling fan, geared to spin at more than 3 times the propeller's rotational speed, was designed to force air through the tightly packed cylinders. Behind the cylinders, cooling gills could be opened or closed to regulate airflow and temperature. German engineers had clearly prioritized aerodynamic efficiency. The tight cowling reduced drag, theoretically improving performance. But cooling an air-cooled radial engine required massive amounts of airflow over the cylinder heads. The BMW 801 had 18 cylinders arranged in 2 rows, and the rear row, tucked behind the front cylinders, was particularly difficult to cool. BMW and Focke Wulf's solution, that high-speed fan and the complex baffling system, represented a calculated engineering gamble. Reduce drag, maximize performance, and trust that the cooling system would be adequate. The American mechanics at Wright Field got the engine running on the ground first, conducting static tests with the aircraft tied down. The BMW 801 rumbled to life with a deep, powerful sound, different from the higher-pitched scream of an American radial. The automatic engine management system, something the Americans found fascinating, controlled fuel mixture, propeller pitch, boost pressure, and magneto timing automatically. The German pilot simply moved the throttle. The engine handled everything else. It was an early form of full-authority digital engine control, decades ahead of its time, executed through mechanical and electrical systems rather than computers. But within minutes of reaching operating temperature, the problems became apparent. The cylinder head temperature gauges, carefully monitored by American engineers, climbed rapidly. The rear cylinders, those tucked behind the front row, showed temperatures that American pilots would consider dangerously high. The oil temperature rose steadily. The cockpit, positioned directly behind the engine with only a firewall separating the pilot from the BMW 801, became uncomfortably warm even during ground runs. Test pilot Captain Robert Anderson was selected for the first flight evaluation. Anderson, a veteran of the 8th Air Force with combat experience against 4-190s over Europe, understood the aircraft's reputation. He'd watched German fighters dive away from combat, disappear before fights could develop into sustained turning engagements. Now he'd find out why from the inside. The pre-flight inspection revealed meticulous German engineering. The fuel system employed self-sealing. Tanks, not as sophisticated as American designs but functional. The armor protection was minimal compared to American fighters. A thin plate behind the pilot's seat and bulletproof glass in the windscreen. The Germans had clearly prioritized performance over protection. The instrument panel was well organized, though metric measurements and German labeling required careful study. Anderson started the engine. Let it warm according to the translated German checklist the mechanics had prepared. The BMW 801 settled into a rough idle, vibrating the entire airframe in a way that felt powerful but not quite smooth. Taxiing out to the runway, the wide-track landing gear provided excellent ground stability. The visibility over the short nose was good, better than the long-nosed P-51 Mustang or P-38 Lightning. The takeoff run was straightforward. Anderson advanced the throttle. The automatic engine system handled the propeller pitch and boost, and the Focke 190 accelerated briskly. Around 90 miles per hour, he eased back on the stick, and the fighter lifted off smoothly. The initial climb rate was impressive. This was clearly a powerful aircraft. The controls felt responsive, precise, exactly as British test reports had described. But as he climbed through 2,000 feet, barely 3 minutes into the flight, Anderson noticed the engine temperature gauges creeping into ranges that would alarm any American pilot. He leveled off at 5,000 feet and began gentle maneuvering to get a feel for the aircraft's handling characteristics. The Focke FW-190 rolled beautifully. The ailerons were light and responsive at moderate speeds. The aircraft felt solid, stable, a good gun platform. Everything the German fighter was famous for, Anderson could feel immediately. This was a pilot's airplane, responsive without being twitchy, powerful without being overwhelming. He could understand why Luftwaffe pilots loved it, but the temperature gauges continued to climb. The cockpit was becoming uncomfortably warm. Anderson could feel heat radiating through the firewall, through the rudder pedals, through the seat. It was like sitting in front of a furnace. The oil temperature was approaching limits that would mandate throttle reduction in any American fighter. The cylinder head temperatures on the rear cylinders were in ranges that suggested imminent engine damage. Anderson reduced throttle slightly, trying to bring the temperatures down. He opened the cooling gills fully, allowing maximum airflow through the cowling. The temperatures stabilized but remained high. He tried a gentle dive, letting airspeed increase to force more cooling air through the engine. The temperatures dropped slightly but never reached what he'd consider comfortable operating ranges. He'd been airborne for 15 minutes. The engine was already demanding careful management, full throttle operations, the kind of sustained combat power American pilots, routinely used in combat, appeared impossible for more than brief periods. Anderson could feel the heat, could see the gauges climbing whenever he added power, could sense the aircraft's fundamental limitation. The Germans had built a fighter with phenomenal performance, but that performance came at a brutal cost. The engine couldn't sustain combat operations without overheating. After 25 minutes of flight, carefully managing power settings and monitoring temperatures constantly, Anderson brought the FW-190 back to Wright Field. The landing was uneventful, the wide gear providing stable touchdown. He taxied back to the hangar, shut down the engine, and climbed out of the cockpit drenched in sweat. The mechanics immediately converged on the aircraft, checking the engine, noting temperatures, documenting everything. The test report Anderson filed was clinical but damning. The Focke W-190, for all its impressive performance characteristics, suffered from a critical operational limitation. The engine could not sustain full power operations for more than 10 to 15 minutes without reaching temperature limits that risked catastrophic damage. Combat required constant maneuvering, frequent throttle changes, sustained high power settings. The BMW 801, in its tightly cowled installation, simply couldn't handle it. Anderson's initial flight test was just the beginning. The Wright Field team assembled a comprehensive evaluation program that would push the captured W-190 through every conceivable operational scenario. They needed to understand not just that the aircraft overheated, but precisely when, why, and under what conditions. The data would need to be specific enough to develop tactical recommendations for combat units facing these fighters over Europe. Lieutenant Colonel Marcus Cooper, the Foreign Equipment Section's chief technical officer, organized the test program into distinct phases. Phase 1 would be ground testing, running the BMW 801 through its complete operational envelope while stationary. Phase 2 would involve controlled flight testing at various altitudes, speeds, and power settings. Phase 3 would simulate combat maneuvers, pushing the aircraft through the kind of violent maneuvering that characterized actual air combat. And if the aircraft survived all that, Phase 4 would involve destructive testing, deliberately exceeding all limits to understand the failure modes. The ground testing phase revealed the engineering compromises built into every component of the cooling system. The 12-blade fan at the front of the engine, spinning at nearly 3,000 revolutions per minute, consumed approximately 30 horsepower just to operate. That was power not available for propulsion, a significant penalty. But without the fan, the tightly cowled engine would overheat even faster. The German engineers had calculated that the drag reduction from the tight cowling more than offset the power loss to drive the fan. On paper, the math worked. In practice, the margins were razor thin. The cooling gills, located at the rear of the cowling, could be adjusted by the pilot to regulate airflow. Fully closed, they minimized drag but provided minimal cooling. Fully open, they maximized cooling but increased drag significantly, reducing top speed by nearly 15 miles per hour. In theory, the pilot could adjust the gills throughout the flight to optimize the balance between cooling and performance. In practice, during the chaos of combat, pilots rarely had the attention or opportunity to manage cooling gills precisely. Most simply left them fully open during combat, accepting the performance penalty to avoid engine damage. Wright Field engineers discovered another problem during ground testing. The oil cooling system, that complex ring-shaped radiator mounted at the front of the engine, directly behind the fan, worked adequately at high speeds when ram air pressure forced cooling air through the system. But at low speeds, particularly during takeoff and landing, or during slow-speed maneuvering at altitude, the oil temperature would spike dramatically. The BMW 801 relied heavily on oil cooling, more so than American radial engines. The oil didn't just lubricate. It carried away significant heat from the engine's internal components. When the oil cooling system couldn't keep up, when temperatures exceeded safe limits, the oil's lubricating properties degraded rapidly. Viscosity changed, additives broke down, and engine wear accelerated exponentially. The American engineers ran thermal imaging tests, using specialized equipment to map the temperature distribution across the engine during operation. The results were striking. The front cylinder row, exposed to direct airflow from the fan, operated at temperatures that were high but manageable. The rear cylinder row, tucked behind the front cylinders, operated at temperatures that made the Americans wince. Individual cylinders in the rear row would reach temperatures nearly 50 degrees Celsius hotter than the front cylinders. This thermal imbalance created stress throughout the engine. Components expanded at different rates. Gaskets failed. Seals leaked. The entire power plant was constantly fighting against its own thermal dynamics. Wright Field obtained several BMW 801 engines from other captured aircraft, allowing them to conduct parallel testing programs. They ran engines to destruction, deliberately exceeding temperature limits to document the failure modes. What they found was both predictable and disturbing. At sustained high temperatures, the rear cylinders would experience valve seat recession, where the valve would gradually sink into the cylinder head, changing valve timing and compression. Piston rings would lose tension, allowing combustion gases to blow by into the crankcase, reducing power and increasing oil consumption. Supercharger, driven directly from the engine crankshaft, would suffer bearing damage from oil degradation. And in the worst cases, cylinders would seize completely, stopping the engine instantly and catastrophically. The documentation was meticulous. Every test run was recorded with instrument readings captured every 30 seconds. Temperature, pressure, vibration, power output, fuel consumption, oil consumption, all tracked and graphed. The data painted a clear picture. The BMW 801 could produce its rated 1700 horsepower reliably, but only for brief periods. Sustained operations at full power would damage the engine within 15 to 20 minutes. Operations at 90% power extended the safe operating time to perhaps 30 minutes. Only at 75% power or below could the engine operate indefinitely without temperature concerns. For combat operations, these numbers were devastating. Air combat was conducted at full throttle. Pilots didn't have the luxury of managing power settings while enemy fighters were trying to kill them. You flew at maximum power, used every ounce of performance your aircraft could provide, and worried about engine longevity later. American fighters were designed with this reality in mind. German fighters, or at least the W190, were not. the Wright Field team arranged comparative flight testing between the captured FW-190 and several American fighters. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. A P-47 Thunderbolt, a P-51 Mustang, and a P-38 Lightning were flown in formation with the German fighter, all aircraft maintaining full combat power, to see how long each could sustain maximum performance operations. The results were exactly as expected, but still remarkable to witness. The P-47, with its massive R2-800 engine and generous cowling design, maintained full power for the entire test duration of 45 minutes without any temperature concerns. The engine ran hot, certainly, but well within design limits. The pilot reported no cockpit heating issues, no need to reduce power, no concerns whatsoever about engine damage. The Thunderbolt was built for sustained combat operations, and it showed. The P-51 Mustang, with its liquid-cooled Merlin engine, performed similarly well. The coolant temperature rose during sustained high-power operations, but stabilized at levels that allowed indefinite operation. The radiator system, located under the fuselage with its ingenious design that actually produced a small amount of thrust from the heated air, handled the thermal load without difficulty. The Mustang pilot reported excellent cockpit comfort and no engine management concerns throughout the test. The P-38 Lightning, with its twin Allison engines, also demonstrated excellent thermal characteristics. The engines ran hot, particularly the turbo superchargers, but remained within operating limits. The twin-engine configuration provided redundancy. Even if one engine developed problems, the aircraft could return home on the other. The Lightning pilot noted some minor coolant temperature concerns, but nothing that would require power reduction during combat. The W-190, by contrast, reached critical engine temperatures after just 14 minutes of sustained full-power operations. The pilot, a different test pilot named Captain James Richardson for this particular evaluation, reported that the cockpit had become almost unbearably hot. The temperature gauges were well into the red zones, and he could smell hot oil vapor entering the cockpit. He reduced power immediately, opened the cooling gills fully, and began a gentle descent to increase cooling airflow. Even with reduced power settings, it took nearly 10 minutes for the engine temperatures to return to safe levels. The comparative test was flown 3 more times with different pilots to ensure the results were consistent. They were. Every test produced the same basic outcome. The American fighters could maintain full combat power indefinitely. The German fighter could not. The implications for combat tactics were profound and would be disseminated to every American fighter squadron in Europe. Wright Field also conducted altitude testing to understand how the cooling problems varied with altitude. The results were complex. At low altitude, where air density was high, the cooling fan and ram air pressure provided adequate airflow, but engine power was also high, producing more heat. At medium altitudes, around 15,000 to 20,000 feet, the cooling problems were worst. Air density had decreased, reducing cooling efficiency, but the engine was still producing substantial power. At high altitudes, above 25,000 feet, cooling actually improved slightly because the engine power output decreased due to thinner air, even with the supercharger working at maximum boost. But there was a catch. The supercharger itself generated significant heat. The process of compressing thin air at high altitude to produce adequate oxygen for combustion created thermal energy that had to be dissipated. The BMW 801 supercharger system added to the overall thermal load, particularly at high altitude where it worked hardest. American turbo-supercharged fighters, like the P-47, handled this differently. The turbocharger was located in the rear fuselage, far from the engine, and used exhaust gases to drive the compressor. The heat was largely carried away in the exhaust stream, rather than being trapped in the engine compartment. The Wright Field evaluation also examined the FW-190's combat radius with the cooling limitations factored in. A fighter's effective combat radius wasn't just about fuel capacity. It was about how long you could actually fight once you reached the combat zone. If you had to reduce power after 15 minutes to avoid engine damage, your combat effectiveness dropped dramatically. The calculations showed that an Focke 190, operating from a base in northern France, could intercept Allied bombers over the French coast, engage in combat for perhaps 10 to 12 minutes at full power, then had to either disengage or risk engine failure. American escorts, by contrast, could fight at full power for the entire duration of the bomber mission, potentially 2 hours or more, limited only by ammunition and fuel. The captured aircraft allowed American intelligence to understand something else crucial about German operational doctrine. Luftwaffe fighter tactics in 1943 and 1944 made much more sense when viewed through the lens of these engine limitations. The Germans favoured vertical tactics, diving attacks from high altitude followed by zoom climbs back to altitude. These tactics were effective against bombers and allowed the engine to cool during the zoom climb phase, when power could be reduced and the aircraft was using accumulated energy rather than engine thrust to gain altitude. The Germans avoided sustained horizontal turning fights at low altitude, exactly the kind of combat that would overheat the engines fastest. American fighter pilots had developed tactics that exploited this weakness without fully understanding it. They'd learned that if you could force German fighters into a low-altitude turning fight, the Germans would typically break off after a few turns and try to extend away. Allied pilots assumed this was because the Focke 190 couldn't turn as tightly as a Spitfire or Mustang, which was partially true. But now, American intelligence understood there was another reason. The Focke 190 pilots couldn't afford to stay in sustained low-altitude combat. Their engines wouldn't survive it. The Wright Field team compiled their findings into a comprehensive technical report that ran to more than 200 pages. The report included detailed performance data, thermal analysis, comparative testing results, and tactical recommendations. Copies were distributed to the 8th Air Force in England, the 9th Air Force supporting the invasion of Europe, the 12th Air Force in the Mediterranean, and to training commands back in the United States. Fighter pilots studied the report, and new tactical guidance was issued. The recommendations were straightforward. When engaging Focke 190s, try to force sustained combat. Don't let them hit and run. Pursue them, force them to maneuver continuously, keep them at high power settings. After 15 minutes, their effectiveness would degrade as pilots had to choose between pressing the attack and preserving their engines. If a German fighter broke off from combat and tried to extend away, pursue aggressively. The pilot might be trying to disengage not because he's won the engagement, but because his engine is about to fail. The intelligence also explained some curious loss patterns the Allies had observed. There were instances where Focke 190s were found crashed in Allied territory with minimal combat damage, the pilots having bailed out or died in the crash. Some of these losses had been attributed to running out of fuel, but post-crash investigation suggested many had suffered engine failures. The cooling problems, the sustained high-power operations during combat, the accumulated thermal stress, it all made sense now. Some German pilots were literally flying their engines to destruction during combat, pushing beyond safe limits because the alternative was being shot down. Over the following weeks, the Wright Field team conducted extensive ground testing, repeatedly running the engine through various power settings and configurations. They tested different throttle management techniques. They monitored temperatures obsessively, documenting exactly when the engine crossed from safe operating ranges into dangerous territory. The pattern was consistent and undeniable. At full throttle, in the kind of sustained combat climb American pilots routinely employed, the BMW 801 overheated within 10 to 12 minutes. The rear cylinders, starved of adequate cooling airflow despite the 12-blade fan, would reach temperatures that risked valve damage, ring failure, and eventual seizure. The oil temperature would climb into ranges that reduced lubrication effectiveness. The cockpit would become nearly unbearable, with temperatures approaching 55 degrees Celsius, hot enough to impair pilot effectiveness. The early production FW1, 90 Aeon, and A2 models powered by the BMW 801C engine, had suffered even worse. The German technical manuals, captured along with various aircraft, documented the problems. Early Ioni engines frequently required replacement after only 30 to 40 hours of operation. The overheating caused premature wear, metallurgical stress, and component failure. Logs, captured from overrun German air bases, showed chronic engine problems throughout 1941 and into early 1942. The maintenance records told a story of constant struggle. Luftwaffe ground crews worked around the clock, trying to keep their 4 190s operational. Engine changes were far more frequent than with American fighters operating in similar conditions. Cylinder replacements became routine rather than exceptional. Oil consumption was significantly higher than specifications predicted. The complex cooling gill mechanism required constant adjustment and repair. Springs weakened, linkages bent. The electric motors that drove the gills would fail, forcing ground crews to jury-rig manual systems or wire the gills in a fixed position. One particularly revealing captured document was a maintenance report from Jagdgeschwader 2, one of the elite Luftwaffe fighter wings operating Focke Wulf 190s in France during 1942. The report, translated by Army Air Force's intelligence specialists, detailed the unit's serviceability rates. In a typical month, JG2 had approximately 60 FW190s on strength. Of those, an average of 22 were non-operational due to engine problems. Another 12 were operational but with restricted flight status, meaning they could fly but not engage in full combat operations due to engine concerns. That left only 26 fully combat-capable aircraft from a wing that was supposed to field 60. The maintenance burden was crushing. American fighter squadrons, by comparison, typically maintained serviceability rates of 70 to 80%. The P-47's R2-800 engine was robust and reliable, requiring relatively infrequent major maintenance. The Mustang's Merlin engine was more complex but well supported, with excellent technical documentation and plentiful spare parts. American maintenance philosophy emphasized preventive maintenance and systematic overhaul schedules. German maintenance had become reactive, constantly responding to failures rather than preventing them. The Wright Field team interviewed several captured Luftwaffe pilots who had flown FW190s in combat. These interrogations, conducted with promises of proper treatment under the Geneva Convention, provided invaluable insights into how German pilots actually managed their aircraft's limitations. Oberleutnant Werner Schmidt, a pilot with 11 confirmed victories who had been shot down over France in May 1943, was particularly forthcoming. Schmidt described the constant anxiety of monitoring engine temperatures during combat. Every German fighter pilot, he explained, developed an internal clock. You knew, instinctively, how long you'd been at full throttle. You could feel the heat building in the cockpit even before you consciously checked the gauges. You learned to recognize the subtle changes in engine sound that indicated temperature stress. You developed techniques for gaining precious extra minutes of combat time by briefly reducing throttle during maneuvers where full power wasn't absolutely necessary. But the mental burden was exhausting. American pilots, Schmidt observed with some envy, seemed to fight with a freedom that Luftwaffe pilots couldn't match. The Americans would stay in combat seemingly indefinitely, pursuing, maneuvering, maintaining aggression for extended periods. German pilots had to constantly calculate when to disengage, not based on the tactical situation but based on engine temperature. It wasn't cowardice, it was survival. Push the engine too hard, and you'd be walking home from occupied France, if you survived the bailout. Another captured pilot, Hauptmann Friedrich Müller, described an incident that illustrated the cooling problems vividly. During an interception of American bombers in March 1943, Müller had engaged a formation of B-17 flying fortresses over the French coast. The attack required a long, high-power climb to reach the bomber's altitude of 25,000 feet. By the time he reached attack position, his engine was already running hot. He made one attack pass, fired his weapons, saw hits on a bomber, then had to break off because his temperature gauges were well into the red zones. But as he tried to disengage, American P-47 escorts bounced him. Müller had no choice but to fight, pushing his already overheated engine to full combat power. The dogfight lasted perhaps 8 minutes, an eternity when you're watching temperature gauges climb toward engine-destroying levels. Müller eventually outmaneuvered the American fighters and escaped into cloud cover, but his engine was running so hot that oil smoke was streaming from the cowling. He nursed the aircraft back to his base at reduced power, the engine running rough, cylinder head temperatures well beyond any safe limits. When Müller landed, ground crews immediately swarmed the aircraft. Inspection revealed severe damage to 3 rear cylinders. The valve seats had distorted from the heat. 2 pistons showed scoring from inadequate lubrication. The oil analysis showed extensive metal contamination, evidence of accelerated wear throughout the engine. The entire power plant had to be replaced, and that particular aircraft was out of service for 2 weeks while a replacement engine was installed and tested. Müller had gotten a kill, probably, had survived combat with American fighters, but had effectively destroyed his aircraft in the process. This was not sustainable. The Wright Field evaluation also examined how the cooling problems affected different variants of the Focke 190. The British had provided data from their evaluation of the captured A3 variant that Oberleutnant Faber had mistakenly delivered to Wales in June 1942. The RAF's tests at Farnborough and Duxford had documented similar overheating issues, though the British hadn't conducted quite as extensive thermal testing as the Americans were now performing. The A4 variant, introduced in mid-1942, had made some improvements. The cooling gills were larger, providing better airflow control. The engine installation included improved baffling to direct more air over the rear cylinders, but the fundamental problem remained. The tight cowling, that signature aerodynamic feature of the Focke 190 design, created a thermal environment that no amount of incremental improvement could fully correct. The A5 variant, which began appearing in early 1943, represented Kurt Tank's most significant attempt to address the cooling problems within the existing airframe. By moving the engine forward 15 centimeters and extending the cowling proportionally, Tank created more space in the engine compartment. This allowed better air circulation, reduced heat transfer to the cockpit, and provided slightly better cooling to the problematic rear cylinders. The improvement was measurable but modest. The A5 could sustain full power operations for perhaps 17 to 18 minutes instead of 15. Better, certainly, but still inadequate for the sustained combat operations the air war now demanded. American engineers studying the captured aircraft understood that Tank had been trapped by his original design decisions. The tight cowling, chosen to minimize drag and maximize performance, had created cooling problems that couldn't be fundamentally solved without redesigning the entire forward fuselage. And by 1941, when the cooling problems became fully apparent, the Focke W190 was already in production. Thousands of aircraft were being manufactured. Retooling factories to produce a substantially redesigned airframe would have cost months of production, and Germany couldn't afford that. So Tank did what engineers often have to do. He optimized and fit within constraints, made incremental improvements, and accepted limitations that couldn't be eliminated. The Wright Field report included a fascinating section comparing the FW-190's cooling design to American fighter cooling systems. The P-47 Thunderbolt, roughly comparable to the Focke 190 in terms of engine power and radial configuration, used a dramatically different approach. The R2-800 engine was housed in a cowling that was larger in diameter and significantly less aerodynamically optimized than the BMW 801 installation. The American designers had prioritized cooling over drag reduction, accepting a small performance penalty in exchange for reliable engine operations. The Thunderbolt's cooling system was almost comically overbuilt by German standards. Multiple air intakes fed cooling air into the cowling. The cowl flaps at the rear were enormous, adjustable through a wide range, giving pilots precise control over cooling airflow. The entire philosophy was different. American engineers assumed pilots would need to operate at full power for extended periods, so they designed cooling systems that could handle that requirement with margin to spare. German engineers assumed combat would be brief and intense, so they optimized for minimum drag during those brief engagements. The P-51 Mustang, with its liquid-cooled Merlin engine, represented yet another design philosophy. Liquid cooling allowed much more precise temperature control than air cooling. The coolant absorbed heat from the engine, was pumped to a radiator located under the fuselage, and the heat was dissipated into the airstream. The system was more complex than air cooling, with more potential failure points, but it provided much better thermal management. And the Mustang's radiator installation was brilliantly conceived, with the air heated by the radiator actually producing a small amount of thrust as it exited, partially offsetting the drag of the radiator scoop itself. The Wright Field engineers calculated that if you could somehow install a BMW 801 in a Mustang-style airframe with proper liquid cooling, the engine could probably produce its rated power reliably and indefinitely. But that would require completely redesigning the engine, adding cooling jackets around the cylinders, designing a coolant pump and radiator system, and fundamentally changing the architecture of the power plant. By 1943, such a redesign was impossible given German industrial capacity and the urgent need for production aircraft. The evaluation did identify one positive aspect of the BMW 801 design. The Kommandogerät, the automatic engine management system, was genuinely innovative. American test pilots were impressed by how the system automatically adjusted mixture, propeller pitch, boost pressure, and timing based on throttle position and altitude. It reduced pilot workload significantly, allowing the pilot to focus on flying and fighting rather than managing engine parameters. American fighters required pilots to manually adjust mixture controls, propeller pitch, and various other settings throughout the flight. The German system handled all of that automatically, but the irony was sharp. The Germans had an advanced engine management system that would have been brilliant for sustained operations, mated to an engine installation that couldn't handle sustained operations. The Kommandogerät was a solution to a problem the FOV 190 didn't have, while failing to solve the overheating problem it did have. American engineers noted this in their report with a certain bemused respect. German engineering was undeniably sophisticated, but sometimes that sophistication was misdirected. The captured aircraft also revealed interesting details about how German pilots attempted to manage the cooling problems through technique. The throttle quadrant included markings that indicated recommended power settings for various flight regimes. Maximum continuous power, the highest setting that could theoretically be sustained indefinitely, was marked at approximately 75% throttle. Combat emergency power, for brief periods only, was marked beyond that, and there were written instructions, in German, on a placard near the throttle. Kampfleistung nicht länger als 10 Minuten. Combat power, not longer than 10 minutes. 10 minutes. The Germans knew. It wasn't a secret or a surprise. The limitation was built into the pilot's operating handbook, literally written on placards in the cockpit. German pilots were officially instructed not to exceed combat power for more than 10 minutes. But combat didn't respect official limitations. When enemy fighters were trying to kill you, when you needed every ounce of performance to survive, you used full throttle for as long as necessary. And the engine paid the price. The Focke 190A3 and later models, with the BMW 801 D2 engine, had partially addressed the cooling problems through improved baffling and larger cooling gills. The A5 variant, introduced in early 1943, moved the engine forward by 15 centimeters, creating more space between the power plant and cockpit. This improved pilot comfort slightly and provided marginally better cooling to the rear cylinders. But the fundamental problem remained. The tight cowling, that aerodynamic efficiency Kurt Tank had prioritized, created cooling limitations that no amount of incremental improvement could fully solve. American engineers studying the captured aircraft understood the implications immediately This explained the tactical behavior Allied pilots had observed. Luftwaffe pilots couldn't engage in prolonged combat because their engines couldn't handle it. The hit-and-run tactics, the tendency to make a single pass and zoom away, the reluctance to dogfight at low altitude where engine temperatures soared even faster, all of it made sense now. The German pilots weren't being cautious by choice, they were being cautious by necessity. Their aircraft, for all its impressive performance, had a built-in timer. Engage, attack, disengage, let the engine cool. Repeat. Any prolonged combat risked engine failure, and engine failure over enemy territory meant death or capture. The intelligence value was enormous. The Army Air Forces disseminated the findings to fighter groups throughout Europe. American pilots learned to exploit the weakness. Force the German fighters to engage in prolonged combat. Make them maneuver. Make them maintain high-power settings. Make them stay in the fight. After 15 minutes, the full 190s would have to break off or risk catastrophic engine failure. P-47 Thunderbolts, with their massive R2-800 engines and generous cooling design, could maintain combat power indefinitely. P-51 Mustangs, with liquid-cooled Merlin engines and efficient radiator and systems, had similar endurance. The Americans could simply outlast the Germans. The psychological impact on Luftwaffe pilots was significant, but rarely discussed in combat reports. Imagine flying one of the world's best fighters, knowing you're sitting in an aircraft that, in terms of pure performance, can match or exceed anything your enemy flies. You have superior roll rate, excellent diving speed, devastating firepower. But you also know that every minute of combat brings you closer to engine failure. You monitor your temperature gauges constantly. You feel the heat building in the cockpit. You know that if you stay in the fight too long, if you push too hard, the engine will fail. Not might fail, will fail. It's not a question of if, but when. This knowledge forced conservatism on pilots who might otherwise have been aggressive. It created stress beyond the normal stress of combat. Every engagement became a calculation. How long have I been at high power? How hot is the engine? Can I risk one more attack pass? The mental burden was exhausting. American pilots, by contrast, could focus entirely on the tactical situation. They didn't worry about engine temperatures during combat. The P-47's cooling system was so overbuilt that temperature management was rarely a concern. The Mustang's Merlin engine could run at high power settings for hours. The W-190's engine problems also affected maintenance operations. The BMW 801 was a complex engine, with its automatic control system, its intricate cooling fan mechanism, and its temperamental behavior. Luftwaffe maintenance crews spent enormous amounts of time managing engine problems. Cylinder replacements were common. Oil system maintenance was constant. The cooling gills required frequent adjustment and repair. In the field, under combat conditions, with limited spare parts and overworked maintenance personnel, keeping FW-190s airworthy was a significant challenge. American fighters, by comparison, were designed for easier maintenance. The R2-800 in the Thunderbolt was a robust, reliable engine that could absorb abuse. The Merlin in the Mustang, while more complex, was well understood and supported by excellent technical documentation and spare parts availability. American maintenance philosophy emphasized interchangeability, standardization, and ease of repair. German philosophy emphasized performance, even when that performance came at the cost of maintainability. The captured FW-190 at Wright Field provided one more critical insight. The Germans had known about the cooling problems from the very beginning. The first prototype, designated Vone, had demonstrated severe overheating during its maiden flight on June 1, 1939. Test pilot Hans Sander had famously commented that flying the aircraft was like sitting with both feet in a fireplace. The cockpit had reached 55 degrees Celsius on that first flight, and that was with the original BMW 139 engine, before the switch to the even more powerful BMW 801. Kurt Tank, the chief designer, had made a conscious decision to accept the cooling limitations in exchange for the performance benefits of the tight cowling. He'd believed, or hoped, that the cooling problems could be engineered away through clever, baffling, efficient fan design and careful engine management. To some extent, he was right. The production FR-190A3 and later models were usable, effective combat aircraft, but the overheating issue was never truly solved. It was managed, mitigated, worked around. But it was always there, a fundamental limitation built into the airframe from the first design drawings. The American evaluation concluded that the Focke Wulf 190 represented a different set of engineering trade-offs than any Allied fighter. The Germans had optimized for performance, accepting limitations in cooling, range, and operational endurance. They'd built a Sprinter, a fighter designed for short, intense engagements. The Americans had built Marathoners, fighters designed for long-range escort missions, extended combat patrols, and sustained operations. Neither philosophy was inherently wrong. They simply reflected different operational requirements and different industrial capabilities. But in the specific circumstances of the air war over Europe in 1943 and beyond, the American philosophy proved superior. The strategic bombing campaign required fighter escorts that could fly hundreds of miles, engage in combat, and still have fuel to return home. The massive air battles over Germany required fighters that could stay in the fight, maintaining combat power for extended periods. The Focke 190, for all its impressive qualities, wasn't designed for that kind of warfare. It was designed for the quick interceptions and local air superiority battles of 1941 and early 1942. By mid-war, the nature of the air campaign had changed, and the Focke 190's limitations became increasingly significant. Luftwaffe tactics evolved to work within the constraints. German fighters would climb to altitude before engaging Allied bomber formations, building up energy and altitude advantage. They'd make slashing attacks through the bomber boxes, firing their heavy weapons, then zoom back up to altitude to let their engines cool before the next pass. The entire tactical doctrine was shaped around the aircraft's operational limitations. When American escort fighters appeared in greater numbers, equipped to fight at high altitude and sustain combat, the German tactical system began to break down. The captured aircraft at Wright Field provided hard data to support what Allied pilots had suspected. The Focke 190, despite its fearsome reputation, had a critical weakness that could be exploited. The dissemination of this intelligence to operational units gave American pilots both tactical guidance and psychological confidence. They knew the German fighter couldn't sustain prolonged combat. They knew that forcing extended engagements would stress the enemy's engines beyond safe limits. They knew that the longer a fight went on, the more advantage shifted to the Allied side. By late 1943 and into 1944, as the air war over Europe intensified, the Luftwaffe 190's engine limitations became increasingly problematic for the Luftwaffe. The introduction of the long-range P-51 Mustang escort fighter in large numbers meant that German fighters faced opposition throughout the entire depth of their defensive zone. They couldn't simply engage, disengage, and let their engines cool in peace. American fighters pursued them, forced them to fight, kept them at high power settings until engines reached critical temperatures. Luftwaffe loss rates increased, not just from combat damage, but from engine failures. Focke 190s that survived aerial combat sometimes didn't survive the return flight. Engines that had been pushed too hard, kept at combat power too long, failed during the descent to base. Pilots who'd successfully broken off from combat found themselves gliding powerless over enemy territory, forced to bail out and face capture. The overheating problem that had seemed manageable in 1941 became a critical liability by 1944. The Germans attempted various solutions. The Focke 190D series, introduced in late 1944, switched to a liquid-cooled Junkers Jumo 213 inline engine. This long-nose Focke 190, nicknamed the Dora, eliminated the cooling problems that plagued the radial-engined models. The liquid cooling system was more efficient, more controllable, and allowed sustained high-power operations without the temperature limitations. But the Dora arrived too late, in too few numbers, to make a strategic difference. Fuel shortages, pilot losses, and the overwhelming numerical superiority of Allied air forces had already determined the outcome of the air war. The BMW 801 engine itself continued to be improved. The 801S variant, introduced in 1944, had better cooling characteristics and could produce 2,000 horsepower. The 801F, still under development when the war ended, was rated at 2,400 horsepower with significantly improved thermal management. But these improvements came incrementally, and the fundamental challenge of cooling a 14-cylinder radial engine under a tight cowling was never completely solved within the basic FW190A series airframe design. The captured FW190 at Wright Field eventually completed its testing cycle and was placed in storage. The aircraft had served its purpose. American intelligence had extracted every bit of useful information, had documented the aircraft's strengths and weaknesses, had developed tactical guidance for combat pilots. The physical aircraft became less important than the knowledge it had provided. Today, the FW190's engine overheating problems are well documented in historical records. Period test reports, captured German technical manuals, pilot accounts, and post-war engineering analyses all confirm the same basic facts. The BMW 801, in its tightly cowled installation, could not sustain full combat power for extended periods without exceeding safe temperature limits. This limitation affected German tactics, pilot psychology, maintenance requirements, and ultimately the effectiveness of one of World War II's most famous fighters. The story illustrates a broader truth about aircraft design. Performance on paper doesn't always translate to operational effectiveness. The W190 looked impressive in terms of speed, firepower, and maneuverability. But the cooling limitations, the 15-minute combat timer built into every flight, represented a critical weakness that no amount of pilot skill could overcome. The Germans had built a fighter optimized for one kind of war, a war of quick intercepts and local air superiority. By mid-war, they were fighting a different kind of war, one that required sustained combat capability and operational endurance. The FW190's design limitations, particularly the engine cooling problems, meant it was increasingly mismatched to the strategic situation. American test pilots at Wright Field, sitting in that captured German fighter, feeling the heat building in the cockpit, watching the temperature gauges climb toward dangerous levels, understood immediately what Allied combat pilots had learned through hard experience. The W190 was dangerous, capable, and in the hands of a skilled pilot, deadly. But it had limits, and in the grinding attrition of the air war over Europe, those limits mattered. Every fighter had weaknesses. The challenge was identifying them, understanding them, and exploiting them. That captured aircraft, sitting in an Italian field in June 1943, had provided the Americans with exactly that knowledge. The W190 would continue to serve throughout the war, on all fronts, in multiple variants. It remained a capable fighter until the last days of the conflict, but it never escaped the fundamental limitation built into its design on the first day Kurt Tank and his team committed to that tight aerodynamic cowling. Performance came at a cost. For the Focke Wulf 190, that cost was measured in degrees Celsius, in cylinder head temperatures, in minutes of combat time before the engine demanded respite. The American pilots who flew that captured aircraft understood the cost, and they knew how to make the Germans pay it. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.